Yes. So in the last lecture, we had started with an introduction to the types of neural network models. So we had looked at the models of neural networks. So what are the different models of neural networks? Feed forward and feedback, right? These are the two categories, two classes of models: feed forward neural networks and feedback neural networks, right? So what is the difference between the two? Difference is that in the case of feed forward neural networks, the output is dependent on the current input which is provided, and in the case of feedback networks, the output is dependent on the previous history of outputs, as well as the input which was given at some time at instant earlier, right? So some memory is involved in the case of feedback networks. No such memory involved in the case of feed forward networks. So these were the two classes of models which we looked at. Apart from this, we also looked at neural processing and the types of neural processing. So what are the types of neural processing? We have classification, the typical usage of a neural network classification. You have associations, right? Auto association and hetero association. What is the difference between the two? First of all, both of these processings, in case of neural processing, you have the network actually is going to store patterns in each of these cases, and the difference is the first in the first case, whenever a pattern incomplete pattern is given to the network, then whatever is the closest associated pattern with that which is already stored, that is given as the output of the network. And in the case of heteroassociation, what happens is there are pairs of patterns which are stored, different patterns. So X maps to Y. This kind of a mapping is there, which is stored in the network. And what you're going to give to the network while testing is some X, which could be distorted, and you get Y as out. So these are the associative networks. Apart from that, classification is a typical task. So in case of classification, you get the class label to which the pattern belongs, right? So that was about neural processing. Apart from that, we also looked at learning. What are the different types of learning that we have in neural networks, and what are the types? Two types, right? Supervised and unsupervised. So in the case of supervised, what is the difference between the two? Supervised learning has labeled data sets, right? Labeled patterns. Okay. And in case of supervised learning, the data or the patterns are unlabeled. So if the patterns are unlabeled, then in that case, uh, how does a network learn? Network learns by some similarity by taking advantage of similarity or dissimilarity of the patterns. So that knowledge it uses to actually classify the patterns, right? So this is what we discuss as far as learning is concerned. And how does a network learn? By adapting its weights. So learning is done by adapting weights or changing weights, right? So we also looked at the general learning rule for updating the weights of a neural network. And what is that learning rule? What is the way? What is the mechanism? How do you update the weights? It is a product of C, R, and X. What is C, R, X? So delta W, or the change in weights that you need to compute, right? It is a product of C, R, and X. What is C, R, and X? What is C? C is known as the learning constant, right? C is the learning constant. What is R? The range of C is between 0 and 1. What is R? R is the learning signal. Okay. So what is and how is R computed usually? It is a function of it is a function of the weighted sum of inputs, right? So you use weighted sum of inputs to compute the learning signal. So learning signal is decided by the weighted sum of inputs. X, what is X? X is the input pattern which is provided currently. So X is a vector basically, which is nothing but the input pattern which is provided to the network. So CRX is a general learning rule. And based on this general architecture of learning, there are different types of learning which we'll be studying. Okay? So the outline for today is we'll be looking at the classical conditioning experiment. Following that, we will look at one type of learning, that is Hebbian learning, and we'll be solving problems on Hebbian learning. Okay, so I just want to show a video before we move ahead, which is based on the classical conditioning experiment. I'll just share my screen. I'll share the video with you. Just give me a minute. Can you hear it?
Pavlov's aim was to discover what caused saliva to flow. He rerouted the salivary ducts to the outside of his dog's cheek so that he could collect and
Yes,
measure
ma'am.
the spittle. Perhaps he thought the production of saliva might be the result of a fixed nervous reflex, like a knee jerk.
5 минут 42,5 секунды.
After taking many measurements of spittle, he confirmed that the dogs drooled automatically when their tongues touched food.
Please observe the video. Huh? I'm going to ask you what you have understood by the video. Please observe it. Try to understand it.
He called the response the salivation reflex.
4,5. Хорошая собачка. Я предлагаю поменять
But
собак.
his work started to run into trouble. As his dogs became familiar with the experimental routine, they started to fill their cheek tubes before Pavlov had a chance to stimulate their tongues. The dogs were learning to anticipate food. Pavlov tried a new technique. He erected screens so that the dogs couldn't see what was going on. Before passing meat through the hatch, he introduced a stimulus that was totally unrelated to feeding. A ticking metronome. At first, the dog dripped saliva into its cheek tube only when the food appeared. But after a number of trials, the dog began to connect the ticking with the arrival of meat. Soon, the sound alone made the dog drool. Eventually, the dog salivated as much to the ticking itself as it did originally to the presentation of food.
Полная. Идите сюда. Что я говорил?
He called this new response the conditioned reflex.
Собака.
Whatever the stimulus, his dogs could soon be conditioned to produce saliva. Pavlov believed that he had discovered how animals learned, even in the wild.
Okay. Yeah. So what did you understand by that video? So that was an experiment which is called as the classical conditioning experiment. Okay, which was performed by Pavlov on his dogs, in 1927. Okay. So what were the observations that you made as per that video? What was the experiment about? Yes, anyone can volunteer? Yes.
I think like the how the dog understands without giving the like what you can say repeating the environment variables ringing the bell and those things to the dog will give the saliva initially it was only giving saliva at seeing food,
Hmm.
but afterwards it was giving saliva only by sound or simulating those similar environments.
Correct. Correct. So what Pavlov did was he actually first this was the experiment. So he just brought food into picture. So at the sight or the smell of food, dogs would salivate. So that is a natural response for this given this input, right? So given this input, that either the smell of food or the sight of food, uh, this input is called the stimulus. He called it the stimulus, the unconditioned stimulus. So given this unconditioned stimulus, the response was to generate saliva, which is the normal response. But what Pavlov did was he rang a bell. So at the sound of that bell or the ticker, whatever was there, um, uh, the dog would naturally not salivate. But when what he did was repeatedly he rung the bell at the same time as that the food was presented to the dog, and at when this experiment was performed repeatedly, what happened is the dog began to associate this bell with the food. Okay, so after repeatedly doing this every time, what happened is the dog actually associated this sound of the bell with that food sight or the food smell. So he called this particular input to the system as a conditioned stimulus, the sound of the bell. So you saw in the video that apart from the bell, he tried with several such stimuli which were not actually responsible for generating the response, but uh, because of this association, dog still salivated after he did this conditioning. So he called this the conditioning experiment. Okay. So, so that was the conditioning experiment that you saw in the video. So food generates the saliva, food plus bell will generate the saliva, and over a period of time, if food plus bell is presented again and again, then at the end of this experiment, only the bell is enough to produce the saliva, to generate the response. So this is the classical conditioning experiment which was done by Pavlov in 1927. And this particular experiment, why are we looking at this experiment, is because this experiment is the basis for the learning rule that we're going to look at, that is Hebbian learning. So Hebbian learning uses this classical conditioning experiment as a basis. Okay, so Hebb's hypothesis is on the basis of this classical conditioning experiment. Okay, so it's the oldest rule, and which was introduced by Donald Hebb in 1949. And what does this rule state? This is the rule. So when an axon of cell A is near enough to excite a cell B and repeatedly or persistently takes part in firing it, some growth process or metabolic changes take place in one or both the cells such that A's efficiency as one of the cells firing B is increased. So, so what is the meaning of this is that whenever, so what in our case, in this classical conditioning, we saw that uh, there is this association, the natural association is between the smell of food, okay, that is the sensory input, that is the smell of food, which actually creates a response, that is salivation. Okay, that is a natural stimulus which is used. Okay, so this, what, why does it generate this responses? Because it makes a very strong synaptic contact. This input, this sensory input, that is nose or the sight of food, whatever it is, either of the two, it creates a response because it makes a very strong synaptic contact. Okay, but if I look at, if I, on the other hand, if I have something which has a very weak synaptic contact, like something like a sound of a bell, that is not actually going to, I mean, in the general case, it's not going to create that kind of a response, because the kind of synaptic contact that is associated in generating the response, that is very weak. Okay, but because of this continuously conditioning, performing this conditioning, what happens is this sound of the bell, this input, this sensory input, that is the ear, the sensory organ is ear, which is going to actually uh, uh, perceive this sound, right, of the bell. This also over time will actually create a strong synaptic contact. Okay, so Again, there are two parts to this rule. The first part says that if there are two neurons on either side of a synapse which are activated simultaneously, then the strength of that synapse is selectively increased. Okay, so if they are simultaneously actually activated, so that is what is happening simultaneously while the food is being presented, the bell is being rung. Okay, so it is increased. If two neurons on either side of synapses are activated asynchronously, then that synapse is selectively weakened or eliminated. So if there is no association, I mean it's asynchronous, then it is eliminated, and that will not have an effect, in fact, in producing that kind of a response. So this is the basis for Hebbian learning, and let us look at it mathematically how we actually make the neuron learn by means of this Hebbian learning. Okay, this kind of synapse is called as Hebbian synapse, and the learning rule, which is Hebbian learning rule, it actually represents a feed forward and unsupervised learning, and it can work for all kind of activation functions. So any activation function we use, so we saw R is a learning signal, R is f of W transpose X, right? Where f is the activation function. So any kind of activation function is used, but what we need to do is we simply need to update the weights by making use of this idea. Okay? That is increasing the strength of the synapse. So basically, synapse is nothing but the weight. When you talk about synaptic contacts that we are talking about in terms of neurons, the biological neurons, these synapses are nothing but the weights, right? So we are going to update the weights by means of this rule, learning rule. So how are we going to update the weights? That we'll see now. So this is the mathematical formalism for Hebbian learning. So our learning signal is f of W transpose X. And in our case, in the case of Hebbian learning, you can go for any f. The activation function f can be anything, any of the activation functions which are available. Okay? And the weight, so weight update is directly CRX, f of W transpose X times X, right? The same thing. Only what we need to do is we simply need to keep on updating the weight. So W, if I'm going to compute new weights, is W old plus delta W, right? So delta W, this delta W that you're computing in case of Hebbian learning is simply CF, COX, right? COX, where O is F of W transpose X. So the activation function applied over W transpose X. Okay? And if you are actually going to train a neural network using this, the weight in initial values of weight are usually small random values around the weight equal to 0. So before learning, when you initialize the networks, it will have some random weights which will be small and random around W equal to 0. Okay. When you look at this capital W, understand that capital W is a weight vector. The small values that you see here is a single weight adjustment. Okay. So if you look at it, so if you look at a neuron, you have these WIs, W1, W2, and so on, right? N weights. This neuron will have N weights. These are the weights, sorry, W1, W2 up till WN. And what you're giving to the neuron is the input, X1, X2 up till Xn. Okay. So each of this weight will be changed. It is adaptive, right? Each of these weights will be changed by means of this rule, Hebbian rule, which is simply COX. This learning signal R is simply equal to the output. And the output is simply activation function applied over weighted sum of inputs. Okay. So to understand how this will work, we will just solve the problem based on this particular rule. Okay. So this is the problem that we need to solve. So what is given to you as input is you have three input patterns, x1, x2, and x3. These are the three input patterns which are presented in the form of vectors, right? x1, x2, x3 represent three input patterns, and these are the initial weights. So W1 that you see is the initial weights which the network is initialized to, and also the learning constant which is there, that is given to be 1. Okay? So given this, you have to use Hebbian learning rule, and you have to find weights after one iteration. What do you understand by one iteration? One iteration is nothing but one epoch. Okay? And one epoch will constitute presenting all the patterns that you have in your data set exactly once. Okay, so you're giving x1, x2, x3 once you form one epoch of training, or you perform one epoch of iteration, one iteration of training, right? So either you call it one epoch or one iteration. So you need to apply Hebbian learning to find the weights after one iteration of training. Okay? And first you do the same using bipolar binary activation function, and the next time you do it, just try it with bipolar continuous activation function. Okay, so let us solve this problem. So first we'll solve it using bipolar binary activation function. Okay, so first step is we need to compute the net value, or the weighted sum of inputs, right? Because your function activation function will be applied over the weighted sum of inputs. First step is you compute the weighted sum of inputs, right? Now, so step one, you give the first pattern. See, there are three patterns with us: x1, x2, x3, which are our three pattern vectors. These are our three pattern vectors, right? Input patterns. So how are you going to update the weights? You present the first pattern to the network, you compute the weights, you adjust the weights, you adapt the weights, you find the new weights, right? You give the first pattern, right? Give the first pattern to the network, this is your network. Give the first pattern to the network, compute the output, okay? Adjust the weights. Okay? Then next step, give the second pattern to the input with the new neural network. New neural network means the weights have changed. Okay? Compute the output, adjust the weights. Are you getting it? Then you give the third, again compute the output, adjust the weights. For adjusting the weights, you are using one of the learning mechanisms or the learning. So in our case, we are using the Hebbian learning. Okay. So for Hebbian learning, what we are doing is first we are presenting the first pattern now. So when you present the first pattern, the first step is to compute net value. This is called as a net value. Okay. What is called as a net value? Weighted transpose of inputs, right? W transpose X is called as a net value. So you have X. This was the first pattern that is there, right? Net value is W1 transpose X, because initial weights are also given to you. So whatever the initial weights are there with the network, you multiply it with the input. Okay. So if you multiply it, what is the value of net? What was W? First of all, let us write W1 is W1. W1 is 1, 1 minus 1, 0, and 0.5. Okay, this is our W1, which is given to us. Now we need to compute net 1. So net 1 is nothing but this 1 minus 1, 0, 0.5 times x, x1, x1, right? This whatever, the first pattern. What is it? What is the value of net 1? And someone tell me what is the value after multiplying these two vectors? You multiply 1 with 1. Yes,
3.
3. Net 1 is 3, right? So now using this net 1, you will apply the bipolar binary activation function, right? On this net value, you will apply the bipolar binary activation function. What is the bipolar binary activation function? Bipolar binary. This one. We collect step function. Okay. This is net value. Okay. If net value is greater than or equal to 0, then it is 1 plus 1. If it is less than 0, it is minus 1. You getting it? This is f of net. Fine. This is the bipolar binary activation function. So using this, we are going to compute all our activation values, the outputs, right? So what is the output? It is sine of net 1, that is sine of 3, which is equal to plus. Correct? So O1 is plus 1. Now using this output, we need to update the weights, right? Using the output, we need to update the weights. So how do you update the weights? We need to write the equation for delta W. So delta W is nothing but C O1 times X. Okay? And what is O1 is given to you, C is 1 and X is the pattern, right? So it is 1 times the pattern. So it is equal to the pattern itself, right? What is that pattern? Whatever the pattern was, I'll just write it. 1 minus 2, 1.5. This is the pattern. Okay. That is delta W. So delta W is a change in weights. Now using this delta W1, we need to update the weights. We need to find the new weights for the network. What are the new weights for the network? You write the weight update equation. What is it? W2 is W1 plus delta W1. W1 plus delta W1. So what is it? Whatever is the initial weight vector that we had, that we add with this, right? So that weight vector is 1 minus 1, 0, 0.5 plus this pattern that we got, delta W that we got. Add these two vectors and you will get the new weights. What are the new weights? Add it. So 1 plus 1, right? Minus 1 plus minus 2. So delta W2, the new weights, the updated weights are these. Okay, this is the new weights. So after you presented the first pattern X1, you use a Hebbian learning rule and you updated the weights. Now these are the weights of the network. Okay, network has changed in the sense that the weights have changed. So now what do? You go with presenting the second pattern. Give the second pattern. Second pattern is this pattern. 1 minus 0.5, minus 2, and minus 1.5. Right? So net 2, now you compute net 2. or this pattern that you have got to compute net 2. So net 2 is W2, the current weights that you have, W2, right? Transpose X. What is it? Take the weights, new weight that you've computed, that is 2 minus 3, 1.5 and zero point 0.5, and the new pattern that you've got, right? 1 minus zero point 0.5, minus 2, and minus 1.5. So what are you getting? The product of these two. What is the answer? What is the value of net 2? It is minus 0.25. Are you getting minus 0.25?
Yes, ma'am.
So now what do you do? The same activation function now you apply to net 2. So f of net 2. So that is nothing but sine of minus 0.25. Okay, that is minus 1. So minus 1 you're getting. Now what you do next step? What is the next step?
Delta W.
Turn, compute the output, find the weight change, right? Delta W. Next step is find delta W. So delta W2 is nothing but C go to X, right? What is it? The X that you have currently, that the sign of all those values will change because your O output is minus 1, right? So the sign will change. What is the answer here? X, this is the current X that you have, right? So sign is going to change. Are you getting this?
Yes, ma'am.
Okay. So once you have this delta W2, you can compute the new weights again. So the new weights are W3 is W2 plus delta W2. So the weights we had earlier, that is W2, that vector you have to use. There, this one. 2 minus 3, 1.5, 0.5. 1.5, 0.5. And delta W2 we computed. That is minus 1.52 and 1.5. Is the answer.
One minus 2.5, 3.5, 2.5.
And 2, right?
Yes.
Yeah. So finally, you give the third pattern. This is the third pattern. So for this pattern, you compute net, right? 0, 1, minus 1, 1.5. Okay. Net is nothing but W3 transpose this weight vector that you have computed, the new weights. W3 transpose X3, X, the third pattern, right? So just write it here for you. 1 minus 2.5, 3.5, 2. This was W3, and this is the third pattern. 0, 1, minus 1, 1.5. So what are you getting? Is
Minus
minus
3.
minus 3, right? So O3 is minus 1, right? Delta W3 is CO3x. CO3x, it's again minus 1. So you have to just make these values, negate the values. That's it. So it is 0, minus 1, 1, minus 1.5, right? That is delta W3. And finally, W4. So W4 is W3 plus delta W3, right? What are you getting? 1 minus 2.5, 3.5, 2, and what is the answer? What are the weights? So add these two vectors. Okay, so it is 1 minus 3.5, 4.5, and 3. Sorry, this is a minus 1.5. This is minus 1. This will be 0. Okay, so these are the final weights. It's W4 are the final weights. So what is the goal of this training? Any problem that you're going to solve, you're going to find out the final weights, right? So whenever you're solving these problems, the aim is to find the final weights after that one epoch of training. That is what you require. That is what you do, in fact, even in the real world. You actually train the network. So you are updating the weights continuously. So at the end of the training, what happens is you have a neural network with the correct weights. Correct weights in the sense that the weights which are going to actually solve the problem. Given a new pattern, unseen pattern, it should be able to classify, recognize it, right? So we're doing it by hand here. We're just solving it and see how it is working. That's it. So these are the final weights. Now we apply the same problem. We have to solve it by using bipolar continuous activation function. What is bipolar continuous activation function? We had looked at these activation functions when we studied machine learning. It is bipolar continuous activation function. Anyone?
Ma'am, are you referring to the bipolar sigmoid activation function?
Yes. It's a
Oh,
sigmoid.
okay. Yes, ma'am. We've heard of it.
Yeah. So bipolar continuous activation function is nothing but the sigmoid function, uh, which is bipolar. Okay. So the range is between minus 1 and plus 1. The range of output values is between minus 1 and plus 1. Right. So what is the equation for that? This is the equation. 2 upon 1 plus e raised to minus lambda net minus 1. Okay. So if you are using this, you have to actually compute O using this function. Okay. Now you have to assume lambda is equal to 1. Lambda is equal to 1. This is a general equation, that is minus lambda net, e raised to minus lambda net. Okay. You have to assume lambda is equal to 1. Lambda is equal to 1. Okay. So again, the same process, only thing is the activation function will change. So x is given to you. This is the first input pattern. We need to compute net. Net we have already computed earlier. What was that? Net was Net was 3. Right? Net will remain the same for the first pattern because the initial weights were the same. Okay. Now what is O1? O1 is basically, right, f of net 1. Now you have to apply this function. So what is O1 now? You have to substitute this 3 in that equation.
Point 905.
Yeah, 0.906. I have it. 0.906. Okay. So C again. Then what we need to do after this? We have computed output. Now we need to update the weights. So we need to compute the change in weights, right? So delta W is nothing but CO1 times X1. So C is 1, O1 is this, and X1 is the input pattern that we have. Okay. If you if you just substitute this, C is 1, so I'm not writing it. It's 0.906 times the vector x1. So x1 is 1 minus 2, 1.5 and 0. What is it? You just have to multiply each term with 0.906. Okay, so first one is 0.906. Next one is twice of that. Okay. Next is this multiplied by this. That is, and finally 0. So this is the change in weights that we have. Using this, we compute W2. So W2 is nothing but W1 plus delta W, right? So just use this delta W1 that we have got and add it to the initial weight vector. Now the weights will change, okay? Even the net values will change because net is net is actually weighted sum of inputs, right? So W transpose X. So W transpose X, W is actually changing. So your W transpose X will also change henceforth. In step 2 and step 3, it will change. It will not be same. Okay. So W2 is W1 plus delta W1. So basically, W1 is 1 minus 1, 0.5. And delta W1 is 0.906 1.0. You add these two, what do you get? That is W2. Okay. First one is 1.906. Next you have minus 2.812. Next is 1.359. Next is 0.5. So this is W2. Okay. Again, use the next step. Only thing is whenever you have activation function which is bipolar continuous or unipolar continuous, then you have to be careful with the calculations. Okay, so just practice this because for the exam you will have to solve such problems. So you need to know how to use your calculator. You need to be quick, otherwise it takes time, and you are bound to make mistakes here. Okay? So set x to x2. This is the second pattern. The same process you have to repeat. Okay? So once you set x to x2, you will get, you need to compute net 2. So net 2 is again W transpose X. So this W2 transpose X, this transpose X. So net 2, right? Transpose X. Multiply these two and find the answer. So you get net 2B minus 0.156, you are getting minus 0.156. Okay. Now this net 2 you need to substitute in the function of O2. So f of net 2 you need to compute, right? A continuous activation function, bipolar continuous activation function, you need to substitute and you get the value of O2. So O2 is basically, when you substitute, you get it to be minus 0.0774. This is what you get. Okay. Then you compute delta W2. So delta W2 again, C times O2 times X, right? CO2X. So C is 1, you just multiply this with X, the current X that you have, that is X2. So once you do that, you get that to be delta W2. Whatever you have got, that minus 0.0774 times X. Okay. You're getting 1 minus point, this was X. You get a weight vector, updated weights is this. Once you do this, you compute the new weights. New weights is, add up these two vectors and you will get the new weight. So the W3, it comes out to be, just write it here, 1.828. Those who are solving, you can check it out. Minus 2 points. I hope you have understood how we are proceeding with solving the problem. I hope everyone has understood that. Anything, you just verify these answers. Then you continue with the third pattern and get the final weights. Okay, the same steps, get the final weights. I'll write the final weights for your reference so that you can find out, check whether your answer is the correct answer. The final weights that you're getting by this activation function is W4 value 1.828. This is the goal, in fact, getting the final weights. Your final weights have to match. Huh? That is important. These are the final weights. W4 is this. These are the final weights. Okay. So this is about solving this problem using Hebbian learning. Okay. There is one more problem which is given here. You can practice it. Okay. There's one more problem for practice. You can solve this at home. Okay. I'll also provide the answers to this. so that you can verify the weights. Okay, the final weight vector I'll be providing for both bipolar binary and bipolar contents. So I'll stop here today. So in the next lecture, we'll continue with the other learning rules that we have.